So last month, Vlad talked about the Y combinator, and there was a lot of discussion whether this had any practical significance or if it was just some academic curiosity or theoretical, had only theoretical importance. So well, first I want to say that all my presentations here at the San Diego user group are on my in a GitHub project, SDPug, and you'll find the presentation from today there too. So I'll start with a problem statement. So I've created a small decorator here, log. Don't get hung up in the code. I can run it. I can illustrate it. Suppose I have some code, and in this code I call a function, in this case re.match, and it tells me I match, but maybe this code is embedded in some functions that I'm not sure are getting called and what the arguments are when it's getting called. So what I do, I put my log around rematch, and now when I call that, I have a log statement saying when it was called and what the parameters to the call were and what the name of the function was. So I don't need to go in and modify the function. I don't need to put any code around it other than just this thing here. But if I want to apply it to a recursive function, and I have here a recursive function, not very original. I think you've seen it before. And now I want to log the call to this function, Fibonacci 0. And it tells me that I called it at 3 a.m. UTC time on January 29th. And I called it with the argument 5. However, the recursive calls that are in when I call this are not logged. I can use this log function as a decorator. And then when I call the same function with the same argument, you'll see that all the outermost call is logged and all the recursive calls are logged. So I want to be able to selectively log some calls, but not all calls. But when I log them, I want to also log all the recursive calls. So I want something in between the decorator that I have here that logs everything, and what I have here that I can select which calls I want to have logged. So in order to do that, I have to write my recursive functions a little bit differently. So here I have a same Fibonacci function, except that the recursive calls, I don't call the function itself, but I call f, where f is just a free variable. And then I place that function inside a fib outer. And the purpose of fib outer is to provide a binding of this free variable f. And then I return the fib inner, because the fib inner is what I really want. So now my hope is if I just pass in the right value for f, fib outer is going to return the Fibonacci function. So what value is that? Well, if I passed in fib inner, then you see that fib inner becomes the recursive definition of the Fibonacci function. But I can't call it with fib inner because fib inner is local to fib outer, so I can't apply fib inner to fib outer. But if I call fib outer with the function that fib outer would return, if I call it with that function, then that would give me the recursive definition of Fibonacci. So in other words, let me just down here. In other words, I want fib equals to fib outer of fib. Now, if I evaluate that, I get an error, a name error, because fib on the right-hand side is not defined. So it's kind of circular, or maybe it's recursive, but it doesn't work. So what happens if I replace the right-hand side with a lambda expression? You know, if you write lambda of x, f of x, that's exactly the same thing as f. So lambda of n, lambda n, fib outer of fib applied to n is the same thing as fib outer of fib. So again, the fib on the right-hand side here is not bound to anything, so you would expect the same name error. But I don't get the same name error. And I can try to run to call fib for all the values in range 11, and I get this output. And so what has happened here is that this is not an assignment here. This is the definition of a recursive function. And the Python interpreter, which is wickedly smart, knows the difference between a regular assignment and a definition of a recursive function. If it had been even smarter, it would have seen that this is a definition of a recursive function, but it's not that smart. So I can rewrite this definition of a recursive function using a def. It's exactly the same thing. And what fib is it's the fixed point of fib outer. That means that if I call fib outer with fib, I will get fib. So, and I can verify that fib and fib outer of fib are the same functions by checking it for all the values of n in range 20. So far, so good. So I'm going to do exactly the same thing, but with another recursive function. I'm going to choose be a little bit more original here and do it with the factorial function. So again, I defined fact inner, where I just replace the recursive call to fact inner by f, where f is a free variable. And then I place fact inner inside fact outer. And the purpose of fact outer is to provide a binding for f. And I return fact inner. So that's fact outer. And then I call, just like before, the same thing I did up here. The only thing that has changed is fib is fact and fib outer is fact outer. That's the only things that have changed. I don't know if I evaluated that. Yes, I did. And I can check that this works. So given that this expression and this expression are almost identical, I could extract a function now that generalizes these two things. So I'm going to call this function fixed point. And it takes an outer function and it returns the fixed point. I'm calling it FP, which takes some arguments and keyword arguments, which are the same arguments that you would pass to the inner function, to outer's inner function. And then it returns outer applied to the fixed point. So I'm going to. So last month we were talking about the Y combinator, and the Y combinator is just a fixed point combinator written in lambda calculus. So I think if you can write the fixed point combinator using recursion in Python, it's much simpler in my opinion. It's easier to understand. I don't know if you agree. So with this definition of fixed point, I can define fib as the fixed point of fib outer and fact as the fixed point of fact outer. And I can verify that I have correct definitions. I can also use the fixed point combinator as a decorator. So here I've called fib outer just fib because I like that name better. And I apply it to a non-recursive function. And it returns a recursive function that has the same name as the outer function. So there are a lot of fixed point combinators. Maybe functionally they are all the same, but they may vary by their side effects and their efficiency. I'm going to give us a couple of examples. Here I have a fixed point combinator that does logging. The definition is exactly the same as what I had up here, but with an additional decorator, log. That's the log function that I had defined previously. And if we apply it to, for instance, a fib outer and to 5, we see that all the recursive calls are logged now, not only the outer call. I can define a fixed point combinator that memoizes. And if I call the regular fixed point combinator on fib on apply to 34, it's going to take quite a long time to calculate. As soon as you see the asterisk here in this box to the left, that means that the computation has started. And when you see a number, it means that it's completed. So I'm starting now. And you see it's computing, computing, computing. And there, it takes approximately 7 seconds. Now, if I apply the memoizing fixed point to fib outer now to 100, I get the answer right away. So memoizing speeds up, and I can just go from a regular fixed point to a memoizing with just applying this combinator. And now, if I want to have a fixed point combinator that both logs and memoizes, the definition is just the same. It's just a different stack of decorators. And now I can apply this to fib outer applied to 10. We see all the recursive calls are logged. And we also see that fib outer is called at most 2 times for each argument. And the second time it calls it here, it just looks up the result in the cache. So that's why it goes so fast. So by writing your recursive functions as non-recursive, but as outer functions, you have a certain flexibility on when you want to apply a decorator, which applies recursively. And so you can think about the fixed point operators as kind of dynamic decorator. And with that, I'm ready to take questions.
I have a quick question. So the one above, like if you just switch the order of decorators, you put memoize before log, you would only see the calls that actually computed something, and you won't be able to see the cached.
I don't know. I haven't tried that. You can try it. Oops.
Yeah, that's good. Yeah,
so a different log. I don't know exactly what's happening here.
No, that's good because that it went in order, like so it didn't call the cached. So it didn't call it didn't log twice, basically, because if it looked up, it will. Okay, that's good.